Today we are going to talk about transformers. To do that, let's go back about 150 years and look at some experiments done by Joseph Henry and Michael Faraday. They were pretty much doing the same experiments, and so we'll talk about them at the same time. And here's what they discovered. Let's take a battery and a switch and a coil of wire. So what they were experimenting with was electromagnetism. It was known by that time that if you run a current through a wire, that there's a magnetic field around that wire. And if we wrap that around some soft iron or silicon steel, depending on what you want to call it, it's going to concentrate that magnetic field. And so they were experimenting with electromagnets. And what Joseph Henry is crediting with discovering is something interesting. He would close the switch, magnet would pick up things, then he would open the switch, and as he opened the switch, there'd be a little spark, right, between the contacts of the switch. And at first he thought, we know electricity is a fluid that's flowing in this wire. It must have momentum. And so when I open that switch, it wants to keep on going and it jumps and makes a spark. But later on he realized what was actually happening is when he closed the switch, got a magnetic field around the coil, and then when he opened the switch, that magnetic field collapsed, and that collapsing magnetic field drove electrons, well, in this direction around the circuit, and caused a high enough voltage to develop across the switch contacts to ionize the air and cause a spark. So it wasn't momentum in the electricity, but it was actually the collapsing magnetic field. The electricity was being induced by the collapsing magnetic field. And so this property is called self-induction. The coil induces voltage in itself from the collapsing magnetic field. And Joseph Henry is credited with discovering this, although Michael Faraday was doing the same experiments around the same time, and so we really don't know who discovered what first. What Michael Faraday is credited with discovering is if we take the same circuit, have a battery and a switch and a coil of wire, and let's put another coil of wire near that coil of wire and have a little spark gap right there. So we close the switch and this magnetic field builds up and crosses both sets of coils. So this coil is enveloped in that magnetic field. And then when we open the switch, not only do we get a spark here, but we get a spark over here. So that means that the moving magnetic field across the second coil was inducing a current in that coil, which caused enough voltage across that gap to ionize the air and cause a spark. And so this is called mutual induction. It's induction in the second coil from current in the first. So Faraday is credited with discovering mutual induction, and Henry is credited with discovering self-induction. So mutual induction is what makes a transformer work. All we need to do is get two coils of wire in close proximity, and the magnetic flux that goes from one coil to the other induces a current in that other coil. So let's put some alternating current on here. And so now we have a magnetic field that's building and collapsing, building and collapsing. And so if we don't have a circuit over here, we're going to get a positive voltage to negative when it's building, and then it's going to flip polarity, negative to positive when it's collapsing. Which side is positive and which side is negative depends on which way the current is going here and which way this coil is wound. There's about 8 different ways you can wind them and put them there and do the current to get different voltages, but basically it's going to be polarized this way one half of the cycle and polarized the other way for the other half of the cycle. Now let's say we have how about 120 volts here, and let's say we want a different voltage over here. Here's the main thing that transformers are used for. I'll erase that to draw it a little differently. Let's put, how about 1,000 turns of wire here, and over on this side, make it, so we can put a voltmeter across here, and we'll put 100 turns here. So 1,000 to 100, or that is actually a 10 to 1 ratio. And what's going to happen is if I put 120 volts over here, I'm going to get 12 volts over here. So I actually am able to step the voltage down. And likewise, I can reverse that if I take a small number of turns here and a lot of turns here. Let's put in 12 volts AC over here. I'm going to get 120 volts AC, assuming that this is a 1 to 10 ratio. So I can step up my voltage and I can step down my voltage. That's the number one thing that transformers are used for. They make the power grid as we know it possible because we generate electricity at a dam or generating plant or something. I think if I understand right, around 600 volts. They'll step that up as high as 500,000 volts, sometimes even at 750,000 volts. And at those high voltages, the electricity can be distributed very efficiently over very long distances. We'll talk more about that when we talk about power distribution. So that's the main purpose of, or main use of transformers, is stepping up and stepping down voltages. Important thing is it only works with alternating current, because if I put DC here, what's going to happen? Current's going to flow, I get a magnetic field, and that magnetic field doesn't change. It has to be moving. So I have to keep that magnetic field moving to induce the current in the secondary. So DC won't cut it. I have to use alternating current, but using alternating current, I can step voltages up, step it up to 500,000 volts, distribute it all the way from the Hoover Dam to Los Angeles, step it back down to 120 volts, and I'm not killing people by having them come within 11 feet of their wall socket. So the construction of a transformer is such that, sometimes the coils are wound on top of each other. One coil is wound and then the other one's wound on top of it. Other ones, the coils are next to each other. And sometimes they might even be on a iron core, which I'll just draw here. And this is kind of rare. One's over here and one's over here, but that's not very efficient coupling. You'll usually find them wound on a bobbin where one is wound on top of the other, or they're wound right next to each other. Now let's take a quick look at how the current works in a transformer. This can be rather interesting. Let's start with our step-down transformer again. So we have a 10-to-1 transformer. And by the way, in the classroom and textbooks we talk a lot about the turns ratio. I'll make that 10-to-1. But when you buy a transformer, they never talk about the turns ratio. We'll talk about how they specify that later. But we use this just to wrap our minds around what the transformer is doing. So it's a 10-to-1 transformer. I'm going to put 120 volts AC. Of course, remember, if I don't specify anything else, that means RMS. And since it's a 10-to-1, I'm going to get 12 volts AC off the other side. Now let's see something interesting here. Let's put, because we can, a 12 ohm resistor here. So what's going to happen? 12 volts AC, I'm going to get an AC current through that 12 ohm resistor of 1 amp. So how much current does it take in this side to get 1 amp in that side? And by the way, this is called the primary. Where we put our voltage in is the primary, and where we take it back out is the secondary. So we have 120 volts AC into the primary and 12 volts AC out of the secondary and 1 amp. Well, looks like we're losing something here, doesn't it? Well, not really, because one thing is preserved from one side to the other. Is we say it's the power is conserved, but there's really no power consumption in here, so it's really improper. So, I mean, I can measure volts and current, so I have 12 volts and 1 amp. My power is voltage times current, so that's 12 watts. But there's actually no power in the transformer. It does not dissipate power. In order to have a manifestation of power, we have to have one of three things: either heat, electromagnetic radiation, or mechanical motion. And except for a little bit of waste heat and a little bit of vibration in here, a very tiny bit, we have neither heat, mechanical motion, or electromagnetic radiation. So there's no power here. We can measure voltage and current, but there is no power. But we go over to here, and now we have heat. So there is a manifestation of power. Power is consumed here. So we actually get the power here. 12 ohms, 1 amp, I squared R gives us 12 watts. Did we lose something? Well, what we lose in one, we gain in the other. So it only takes 0.1 amps in the primary to give me 1 amp in the secondary. So I'm stepping down the voltage, and so as my voltage goes down, my current goes up. So I only need a tenth of an amp in my primary to get a whole amp in my secondary. So my power is conserved. More properly, my volt amps are conserved. Because in a transformer, we don't talk about power because power is not consumed, so we talk about volt amps. So what's power? Voltage times amps. But there's not really power here, so we call it volt amps. Over here, there really is power because we have heat, so we do call it watts. So we have 12 volt amps over here, and we have 12 volt amps over here. So at this time, the transformer is delivering 12 volt amps, which becomes 12 watts over here. But notice we stepped down, our voltage went down, but our current went up. Now, what controls the current is going to be the load over here. So right now I have a 1 amp load, and so I have 12 watts, and so I have 0.1 amps over here. But what's going to happen if I change this to, let's make it 24 ohms. That's going to cut this down to 0.5 amps, and this will become 0.05 amps. So changing the amount of current in the secondary changes the amount of feedback going from the secondary back to the primary and actually controls the amount of current. But my current will always be the same turns ratio, but if I have a step down, my current steps up. If I have a step up, my current steps down. Okay, so what types of transformers are there? I just talked about the step up and step down transformers. So a step up transformer, I have fewer windings in the primary and more windings in the secondary. So I have a turns ratio of 1 to 10. I get a step up, 10 to 1 step up in voltage. If I reverse that, I have more in the primary and fewer in the secondary. Let's say that's a 10 to 1. Then I'm going to have a drop, a 10 times drop. 120 here, 12 here. 12 here, 120 there. So that's your step up and step down transformers. That's ones we think of most often. But another type of transformer is for DC isolation. So, as I mentioned earlier, direct current doesn't go through a transformer. So let's make these coils the same. Now, an isolation transformer doesn't have to be a 1-to-1 ratio. So basically 120 volts in equals 120 volts out. But usually isolation transformers are a 1-to-1 ratio. And the purpose of them is primarily, as I mentioned, a DC component over here will not transfer to the other side. So if I have some DC offset or DC noise or whatever, it's not going to transfer to the other side. So it isolates one side from the other. Another purpose of isolation transformers is safety. Let's just look at the secondary over here. So I have 120 volts in, 120 volts out. And over here, somewhere this is grounded. I'll just ground that there. Let's say that's the neutral wire, that's the hot wire. I go into more detail on this stuff in another video that I have linked below. But here I have a ground here, and here's me also connected to ground. Well, if I touch this one wire somehow, and I'm going to ground, I get 120 volts across me. But on the secondary, I have to actually touch both wires. Since neither of these wires go to ground, my voltage is between that wire and that wire. In order to get a shock, I have to put, a hand there and a foot there, which is very unlikely, especially when things are double insulated and whatever. So if I have an isolation transformer, if I'm connected to ground, well, that's dangerous to touch one wire on the hot side, but over here where it's delivering the current or delivering the power, I have to actually somehow touch both of them to get a shock. So it's a measure of safety there. I'll go into more detail on that in another video, which I have linked below. Another type of transformer is impedance matching. So we have a couple of circuits that we talked about input and output impedance back in DC. So let's say I have a circuit over here that has a high impedance. And I need to connect to a circuit that has a low impedance. What can I do? Well, with the proper adjusting of the turns ratios, I can match the impedance of one circuit to another. So this transformer is designed so that the primary has a high impedance and the secondary has a low impedance, and so I can match the two circuits. A very common place to find this is in radio transmitters, where we have a low impedance transmitter which is pretty common, and the antenna, which is, let me just get this out of the way here, is an end-fed monopole and has a high impedance. So at the bottom, we'll have a little transformer, just a few turns of wire on a toroid that can match the low impedance to the high impedance antenna. Very commonplace. Another place I've seen them is in audio systems where we have to match a high impedance microphone to a low impedance amplifier or vice versa. So we can use transformers for impedance matching. Now, so far we've looked at transformers that have a single winding for the primary and a single winding for the secondary. We can have transformers with multiple windings. And we can have different turns ratios for the different windings. In fact, we can have fun such as, let's say, 120 volts in and 6 volts, 6 volts. Tie them together, you get 12 volts. And so we can have either two separate 6-volt circuits or one 12-volt circuit. Not uncommon at all to have tapped secondaries. Same idea. So a total of 12 volts, but 6 volts here, 6 volts there. And this can be used in multiple ways, like to make a dual power supply. This could do one half of the power supply, that could do the other half of the power supply. And another common thing is might have tapped primaries, because what if we need that? This can work one half of the primary on 120 volts, or if you have a 240 volt circuit, you can use the entire primary. So you might find primaries with taps here and there. You might find secondaries with taps here and there. One thing that was very common back in the days of old tube circuits, you could have a secondary that would have like 6 volts to power the filaments in the tubes, and then 300 volts to power the plates. So that's just one secondary to give you 2 voltages. Another type of transformer is called the auto transformer. And this would be a single coil that is tapped. Very common in older cars to have the ignition coil, which is actually a transformer. It's an auto transformer where we send out a pulsing 12 volts here, and we get about 10,000 volts off of the secondary. So we get the mutual induction. Even though it's a single coil, we still get mutual induction. We just tap it here. There's a type of auto transformer, brand name is called a variac, where this is actually variable and it goes the other way. We have 120 volts here in the Americas, and we have a slider here that can go anywhere from 0 to 120 volts. Don't confuse that with an isolation transformer. They do have variable isolation transformers. But the variac, which is a brand and name, so I'll put my little trademark thing there, actually it's not an isolation transformer, so don't confuse it with an isolation transformer, but it's a variable output, which is an auto transformer, just one winding, and we just put a slider along there to get the proper output. And so one coil, but it acts like two, because we still get the mutual induction from this half down over to that half, and vice versa. There's a type of transformer you may have heard of as a Tesla coil, and that is a type of auto transformer. So we have an auto transformer that is just the right length to tune to a particular oscillator frequency. We have that oscillator driving it, and we get a very high voltage, and it's very efficient because of the resonant frequency. We'll talk about those kinds of things down the road. What is resonant frequency? Well, basically the energy in this transformer wants to get into a synchronicity where it goes back and forth at the same rate as the oscillator, and it ends up kind of building on themselves. And we get some very efficient stepping up of the voltage. So that's a Tesla coil. So let's talk a little bit about efficiency before we move on. Transformers are very efficient in transferring energy without losing it in some form or another. So I think your good high quality power distribution transformers have a efficiency of something like 99.7% or something like that. What that means is I put power in, volt amps go in, and volt amps come out, and we don't have a lot of heat coming out. We don't have a lot of mechanical motion, so you don't hear a lot of buzzing in there from the vibrating. And what whatever else might, mainly it's heat and mechanical motion, because we don't get electromagnetic radiation from transformers at all. So where do we get losses? Well, one thing I haven't mentioned yet is how we build the transformer. They're usually built on an iron core. So here's the iron core. Well, let's look at what's more realistic. They usually show you like this in textbooks. There's a coil there, there's a coil there, and there's an iron core. But in reality, they make what's called a laminated core, and they have these sheets of metal that are shaped like the letter E. And we'll put these opposing each other. And you take the bobbin that has the two coils on it, and you put it in the middle, and you put these together, you slide them together, and you have layer and layer and layer. So layers and layers and layers and layers and layers, and they overlap, and then you have some caps on the end, so that each E becomes something like this. If I can draw it. So there's your bobbin, and then the next one is opposite way, so you get this alternating back and forth, or it could just be one way and just put the cap on it. But the main thing is it's laminated. The reason they laminate the steel, of course, the reason the silicon steel, or soft iron as it's sometimes called, is put there is to concentrate the magnetic field and make it more efficient. But there's a problem. Steel is conductive. Don't we have a magnetic field around a conductive material? Aren't we going to get electric currents in that conductor? Yeah. So the reason they laminate it, we get very small eddy currents in there. Those eddy currents produce heat, and so if we reduce them as much as we can, we have less heat, and so we don't lose a lot in the core. We do have some core losses. It's laminated to reduce those. So another one is copper loss, which is just simply we have current going through copper. Copper is resistive. We're going to get a certain amount of power dissipated as that heat in the wires, so there's a little bit of loss in the copper itself. That's called copper losses. Another one is called hysteresis. This core gets magnetized one way, then magnetized another. We use silicon steel or soft iron because it doesn't hold the magnetism, but every time that flips, it takes a certain amount of energy to cause it to flip the other way, and that produces heat, and that's called hysteresis. So we flip the magnetic field one way, we try to flip it the other way, it resists, and then snaps. And that resisting of flipping the magnetic field is called hysteresis, and it does produce a little bit of heat, so we have a little bit of hysteresis. We use silicon steel because it doesn't hold magnetism, which reduces that hysteresis. And one more loss would be actually the physical vibrating of the core could produce heat. That's another type of loss we have, but they're very, very efficient. And so transformers can take a certain amount of volt amps here, transfer them over here without producing a lot of power and losing that as heat, and then delivering power to our load. And finally, last but not least, how do we specify transformers? When we talk about them in the classroom and in the textbooks, we often talk about the turns ratio, but you never ever see that. I don't think I've ever seen that in a specification. Maybe they do, I've never seen it. How do they specify a transformer? They'll specify it by the input and output voltage. So we have your primary and your secondary, and let's say our primary, they expect you to put in 120 volts, and the secondary would be 12 volts. So they're going to rate that as probably a 12 volt transformer here in North America, because we know it's going to be 120 in. So I go buy a transformer, I say I want a 12 volt transformer, and they just assume it's 120 in. Of course, you go to Europe where we have 240 volts, is going to be assuming they're going to have 240 volts in. So one is the output voltage. So we have a 12 volt, or it might be specified as a primary of 120 volts and a secondary of 12 volts. Either way, input voltage and output voltage, or just the output voltage. And then as far as how much current it handles, sometimes they specify it as a particular output current. Let's say 2 amps. So it says the secondary can handle 2 amps, or it might say 24 VA. 24 VA is the same as 2 amps. So you have to kind of figure that out. If I want to have a certain amount of current in my secondary, and my transformer says, oh, you have a 24 volt amp transformer, I have to calculate that out, knowing that, of course, my volt amps is going to be volts times amps. So I take my 2 amps times 12, gives me 24 volt amps. So I have to use that formula to kind of figure out what my transformer is if it's specified in volt amps. So you're going to get a secondary voltage, possibly a primary voltage, and then either a secondary current or a number of volt amps, depending on the transformer you get. So you just have to, when you specify a transformer, how are they specifying it? As primary and secondary, or just secondary, in which case you have to assume the primary, depending on whether you're in Europe or North America. And in the number of amps, now the amps is easy, but they might specify it in volt amps, so you have to do a little math magic to figure out what your current is if they specify volt amps. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.